Hi everyone, in this video I'll show you how to create the hit mobile game Flappy Bird in under 10 minutes with Bevy and Rust. This whole project, including the source code and assets, are linked in the description, so if you need to reference anything, go ahead and take a look at that. Alright, without any further ado, let's begin. This whole project is only about 200 lines of code, so I think it's definitely beginner friendly. Before you start this tutorial, you should be able to have already set Bevy up. If you don't know how to do that, I'll link the Bevy setup page in the description. Starting off in our cargo.toml file, we're going to be using Bevy version 0.15 for this project, which was just newly released yesterday. Also, we need a way to generate random numbers, so I also decided to include the create rand. Next, create a folder called assets. This is where we'll be putting all of our images and sprites. I would recommend you use my assets linked in the description before you try making your own, because it guarantees that the code will work correctly. Once you've figured out how the code works, you can make your own assets and adjust the code accordingly. Okay, let's start coding. Go into your main.rs file and include Bevy as a dependency. Now let's construct the actual Bevy app. Let's add in the default plugins that will actually make the window and perform lots of crucial tasks. Now let's set some parameters. We want to change the resolution of the window to be square, because the Flappy Bird window is square. To do this, we need to modify the window plugin that's part of the regular default plugins. You can also set other parameters such as the title of the window and the position of the window here, if you so choose. But what's important right now for us is just the resolution part, which you can see that I set right now. By default, the sampling mode for Bevy is linear, and this will make pixel art really blurry. So we need to change the sampling mode to nearest, and we can do this by modifying the image plugin, which we use another set statement for. And this code should successfully open a square window. Obviously nothing is going on yet because we haven't coded any gameplay, so let's start doing that. Let's add a setup system which will run on startup and which will do, as the name implies, set up our level. We'll include an asset server resource which will allow us to load images, and a commands variable that lets us spawn entities. When we spawn the player, we're going to need a component to mark that it is the player. So let's create a component called bird and make it have a velocity parameter. This velocity variable will be in charge of controlling vertical movement. And let's just change the background color to a light blue, because right now, gray doesn't really seem very Flappy Bird-esque. To actually render anything, we need to spawn a camera. We don't need to do anything special because our camera is just staying in place the whole time. Then let's spawn in the actual player with a sprite component. Bevy 0.15 actually switched from using a sprite bundle to this new type of syntax where the sprite is just a component that you can add in. Let's also add a constant called pixel ratio because we don't want the bird to be really small, and let's scale the bird by this amount. Basically, each pixel that we drew in our sprite editor will be this times amount larger on screen. Also, splat is just a quicker way to write the same value in all the fields of a vector. In this case, x, y, and z would both contain the variable pixel ratio. And you can see that we have a bird sprite at the middle of our screen. So our bird isn't really doing anything, and that's kind of boring. So let's add a system called update bird, which will actually make it fly up and down. This system runs every frame, and this is how we're going to be updating the movement of the bird. First, let's query for any entity with a bird component and a transform component. In this case, there's only one. We also need a time resource that will let us get the delta time. This is so we can make stuff run the same at every frame rate. And of course, the keys resource will just be responsible for input. Now, since there's only one bird that will be in the scene, we don't need to do a for loop query, and we can just do an if query for a single bird. And once the space key is pressed, we can set the velocity to a constant value that we'll define later. And of course, we need to make sure the gravitational acceleration is accounted for. You can see how the time resource is important now. Then every frame, we need to integrate the translation by the velocity. And to get that velocity-based rotation that Flappy Bird has, we can restrict the angle between -90 and 90 and make it based on the vertical velocity of the bird with a modifier. And finally, we just need to define the constants that we use in this system. If we run the code now, we should have a bird that flaps up and down when we press space. Okay, now it's time to implement the pipes, which will be the actual obstacles in the game. But first, let's define some constants. Obstacle amount will be the amount of obstacles that we spawn, but they'll be looped anyway, so this number doesn't need to be too large. We'll have a width and height variable that will just be how tall and how wide the image is. You can find this in your sprite editor. In this case, we'll be using 32 and 144. The vertical offset is how much we're going to be displacing the pipes random. The gap size is how large the gaps are that the bird flies through. The spacing is how far the pipes are from each other. And finally, the scroll speed is just how fast they're going to be moving. Let's also define a resource called Game Manager, which will be responsible for storing the image of the pipe and the dimensions of the window. Instead of just going into writing code for spawning the obstacles, let's create some functions for doing so that it's cleaner to do so. By passing in important references like these, we're able to create helper functions that are able to perform tasks such as loading and spawning stuff in. Later on, we'll be calling the spawn obstacles functions to spawn in the obstacles. But we also need some other helper functions such as generate offset, which will generate a random vertical offset for the pipes. Within the spawn obstacles function, we can loop to the obstacle amount in order to generate that amount of obstacles. Each time we'll generate a Y offset, as well as calculate where the pipe should be on the X-axis. Now we have all the information that we need to actually spawn in an obstacle, so let's create a helper function to actually spawn in individual obstacles. We'll take in a translation parameter, a pipe direction parameter, and then the pipe image and commands parameters. The pipe direction specifies whether this is a pipe on the top of the screen or the bottom of the screen. And as we did with our player, we can also spawn in a sprite component with a transform component to represent the pipe. We also need an obstacle component so we can identify this entity as an obstacle, and we'll be defining that structure right now. This will just contain a pipe direction variable because that's all we really need to identify the pipe. Then we can call our spawn obstacle function inside of spawn obstacles. We already know the exact X position, but we're going to need to calculate the Y position based on the pipe direction and the gap size that we defined above as a constant. Since our sprites aren't spawned by their bottoms and their tops, but rather by their centers, we need to calculate the position where the sprite's bottom is at the center of the screen. Then we can add in the random offset and the gap distance to create a pipe obstacle. All we have to do is flip this position and apply the gap distance differently for the pipe that's on the bottom instead of the top of the screen. Additionally, we'll probably also have to flip the sprite. This can be easily done by just scaling the sprite though, in the opposite direction. Now that we've created our helper functions, we just need to call it. You'll notice however that the last two parameters are missing, and we need to actually define these. We'll query for the window component of the primary window to get the width and height of the window, and let's just load the pipe image in with the asset server. Let's also initialize the game manager so that we can use the pipe image later. It's also helpful to store the window dimensions because those might also be helpful later and we don't want to keep querying for the window. With this information, we should be able to spawn in the amount of obstacles. We've pretty much done all the hard work at this point. Create an update obstacles function. This function will be responsible for moving our obstacles and also looping them when they reach the edge of the screen. Each frame, every obstacle is moved to the left of the screen by a certain speed. Then we check if it's exited the left side of the screen, and if it has, we'll generate a new Y position and also reset the X position to the last obstacle in the list of obstacles. Now we have to check if the game is over by checking to see if the bird has touched an obstacle or if it has fallen off the screen. This should be relatively easy to understand. First we check if the bird has fallen lower than the bottom of the screen using the window dimensions variable that we set earlier. Then we iterate through all the pipes to see if the bird is colliding with them using a bounding box algorithm. If any of these conditions are satisfied, we'll set the boolean variable dead to true. And once this is triggered, we can restart the game state by resetting the position and various other variables. We also need to iterate through the obstacles and despawn them while also spawning new obstacles, which is relatively easy due to our helper functions. Anyways, that's it for this video. See you guys in the next one.